Morning, everyone. What are we listening to today? Somebody asked me favorite 80s band. Yesterday, there was some hesitation because I know what characterizes the 80s for me, so we're gonna listen to that. I'm just setting something up here. Yeah, so for me, Diamond Dave really embodies the 80s. So let's have a listen. What's that sound? Here she comes, go back down there. I see you, burning down the avenue. Don't you know she's running home with you? You want to be we're running a little bit hot tonight. I can barely see the road from the heat coming up. Reach down between my legs, ease the seat back. She's running, I'm crying, right behind me, we'll be now. Got the feeling, but I was hearing, 55, ain't no stopping now. everyone. Zach will do your question next. The current expectation is that we still have in-person exams for this course. I don't know any more than you do. I am not informed of anything ahead of time. So if there's talk of changing that, I'm not in the know. So right now, no date for the midterm yet. You can expect end of October. So it's still very far away. We will for sure inform you at least 2 weeks in advance. Several people had the following question. It's a question that has come up on the web work as to whether, right, I'm going to ask you to give me that question because I don't have the book with me. So several people have asked about this question on web work. Can a graph intersect a vertical asymptote? Of course, it's just a yes or no answer. So people said no, and then they got it wrong, and then they changed it to yes, with questions that followed. So a lot of people were under the impression that a graph cannot intersect a vertical asymptote. Well, what's the definition of vertical asymptote? I've given it to you right here. X equals A is a vertical asymptote if the limit from the left is some sort of infinity, or the limit from the right is some sort of infinity. So let's draw a picture. Here, A is going to be, sure, Elliot is suggesting a piecewise defined function. Without drawing anything else, A, by definition, is a vertical asymptote. And then you're done. All right, here you've crossed the vertical asymptote. The function is defined at A, so you have crossed it, right, when viewed coming from the other side, and there's no issue. So there's your counterexample. Here's why a graph can intersect a vertical asymptote. Somebody had asked a question here. Zach wants me to do section 2.3, number 31. Prove that the limit as x goes to 2 of x squared minus 1 is 3. Well, first of all, you know it's 3. Anna wants me to explain why graphs are able to cross horizontal asymptotes. We haven't defined a horizontal asymptote yet, so let's wait until we do that. It's going to come up very shortly. So it's coming up soon. And we'll address that. It's -2, Zach. Thank you. Not that it matters, right? mean, whether it was 2 or -2, it's going to be the same. It's going to be the same proof. It's going to be the same proof. And you know, I mean, I'm very happy that you attempted that question. It's a very nice question. And they want us to prove it using the epsilon delta definition. So let's do it. Using the epsilon delta definition, let's write down what needs to be proven. We need to show that epsilon greater than 0 given, there exists a delta greater than 0 such that if x minus a, so x minus -2 is less than delta, then f of x minus that limit is less than epsilon. This is what needs to be proven for some delta. Daniel wants an explanation of the epsilon delta business. Adele, I'm going to need you to tell me what number 37 is. So before we prove that, from the graph, the idea is this, right? Remember the definition of limit. A function can be made arbitrarily close to L by taking x sufficiently close to a. So the x's you're taking from here, and we're saying f of x is going to be very close to L. So, right, f of x can be made arbitrarily close to L by taking x sufficiently close to a. So mathematically, observe what's happening. F of x can be made arbitrarily, that's the epsilon here. The epsilon is the arbitrarily close to L, right? So f of x minus L is less than epsilon, so very close. F of x is very close to L by taking x sufficiently close to A. So the difference between x and a is very small, sufficiently close. The delta is the sufficiently close. The epsilon is the arbitrarily close. So let's concentrate on this x squared minus 1 minus 3 business, which is, of course, x squared minus 4. It's f of x minus L. Lauren was asking, why is it x squared minus 1 minus 3? Because it's f of x minus L. F of x minus L. So we have this, which factors as x minus 2, x plus 2. And observe that x plus 2 is exactly what you have here, right? This is x plus 2. So this x plus 2 is less than delta. Why is this thing present in here? Remember the definition of limit, we don't want x to be equal to a. Right? If x was equal to a, this would be 0, and we don't want it to be 0. We want it close to a, but not equal to a. Why do we need to put in an absolute value sign? Because it could be on either side. And that, an absolute value takes care of that. Where did the x squared minus 4 come from? Well, I mean, it's x squared minus 1 minus 3. Fabian is asking, what about x minus 2? Well, right. So you see, we have the x plus 2. The x plus 2 is what's going to make, is what's going to allow us to make everything very small. But as you're pointing out, you've got a problem with x minus 2. That is still there, and we don't want it there. We don't want it there, right? So first of all, let's split this up into x minus 2, x plus 2. So this can be made very small. And the hope is that this isn't going to be much of an issue. So for people who've tried this question, I strongly suspect you've made it up to this point. And now you don't know what to do with the x minus 2. Eddie is suggesting x minus 2 is less than x plus 2. Maybe. Maybe it is. You'd have to prove that. You'd have to prove that, and I suspect you can prove that easily. But, right, the idea, what are we doing? We're looking at the limit as x goes to negative 2. So we're in a negative x region here. So actually, I think you might, well, at least in absolute value, you might run into some problems, Eddie. But let's not worry about that for now. Here's how we're going to tackle that. We want to restrict our attention to values close to negative 2. So this business, the x minus 2, is going to be close to negative 4. It's not going to be huge. And that's the beauty. Assume that x plus 2 is less than 1. Let's start with this assumption. I can already hear complaints. How do you know? How can you make that assumption? Let's hold off on that. Let's just start with this assumption. So x plus 2 is less than 1. What does that mean? That means that x plus 2 is between negative 1 and 1. Now, what I want is an x minus 2. I want to know how large x minus 2 can actually be. So subtract 4 from both sides. Subtract 4 from both sides, or add negative 4 to both sides. It's a better way of seeing it. Add negative 4. So you get negative 5 less than x minus 2 less than negative 3. And negative 3, as you know, is much less than 5. So this is really saying minus 5 is less than x minus 2, which is less than 5. In other words, x minus 2 in absolute value is less than 5. Why do we subtract the 4 or add the negative 4? I'm looking to get rid of this x minus 2 in absolute value. So I want an x minus 2 in the middle. And I've succeeded. This, if x plus 2 is less than 1, then this thing is going to be less than 5. Where did the minus 3 come from? It came by adding negative 4 to everything. Negative 1 minus 4 is negative 5. X plus 2 minus 4 is x minus 2. and 1 minus 4 is negative 3. If x plus 2 is less than 1, how do we know it's greater than negative 1? It's the absolute value of x plus 2, which is less than 1. Where did the 5 come from? Well, we are hoping to get the same thing on both sides so that we can conclude that the absolute value is sandwiched. So you see, we can now get rid of this x minus 2. This x minus 2 is less than 5. Where can we study the epsilon delta method? It's in the book. It's in the book. It's where we are now. So you see, by making x plus 2 less than epsilon over 5, now the squeeze theorem, it's the epsilon delta definition, right? So by making this less than epsilon over 5, you have succeeded in making this less than epsilon. So this is going to be valid if you take delta to be epsilon over 5, but we also assumed that it was less than 1. So let delta be the minimum of 1 and epsilon over 5. You need this to be satisfied as well as this. So by taking the smaller of the two, you're good to go. What's the value of epsilon? You don't have control over epsilon. Epsilon is given. It's the delta that you have control over. How did you get delta is epsilon over 5? Well, I mean, we need this whole thing to be less than epsilon. So that's going to work if this is less than epsilon over 5. A beautiful question. A beautiful question. The difficulty lies in the x minus 2. Can we do another question? Somebody had a question up there. Miriam was asking us a question very similar to this, so I'm going to let you work that out. Adele. Adele had a question different. So let's do Adele's question quickly, and then we'll move on. Adele, page 113, number 7. No, sorry, it's Miriam. Where's Adele? If 4x minus 9 is less than or equal to fx, which is in turn less than or equal to x squared minus 4x plus 7 for x greater than 0, find the limit as x goes to 4, is it? 4 of f of x. So the solution, somebody was asking here, delta is the minimum of 1 in epsilon over 5. All right, so we're looking for the limit as x goes to 4. And, you know, I mean, we don't have any other information on f except that f satisfies this inequality. So, I mean, you're thinking to yourself, squeeze theorem. Absolutely, Robert, thank you. I mean, it better be, right? Because we don't have any other technique. As x goes to 4, this is a polynomial, right? So this is easily seen to go to 16 minus 9, which is 7. As x goes to 4, this is a polynomial, so you can just plug in. 16 minus 16 is 0, plus 7 is 7 as well. So by the squeeze theorem, this has to go to 7. We're done. Zoe still doesn't understand where the 1 comes from. The 1 comes from here, right? We assumed that this was less than 1 to see that this thing could be made less than 5. Let's take another example. Last time I told you that all of the limit laws could be proven using this epsilon delta definition. In particular, the limit of the sum is the sum of the limits. Does minimum 1 at epsilon over 5 mean either 1 or epsilon over 5? It means the smallest of the two, absolutely. Yeah, James, 7 it is. 7 indeed. Where did we get 5? Well, I mean, we have it right here. We have sandwiched this x minus 2 between negative 5 and 5, which means that absolute value of x minus 2 has to be less than 5. Jack is asking, can we use the limit laws? The answer is no. We're proving the limit law. We're going to prove this first limit law using the epsilon delta definition. And let's prove it. Let epsilon greater than 0 be given. What does this mean? F of x, the limit of f of x is L, means there exists a delta 1 greater than 0. Fabian is asking for another limit law. We can prove it after. There exists a delta 1 greater than 0 such that if x minus a is less than delta 1, then f of x minus L is less than epsilon over 2. Right? By definition of the limit. Here I'm taking the epsilon to be epsilon over 2, right? So there exists a delta 1 such that if this is true, then the difference between these is less than epsilon over 2. Similarly, there exists, right, since the limit of g is m, there exists a similar one for m. Bethany is asking, what do we mean by epsilon is given? It's just given. But the real question is why over 2? Let's just go with it. You'll see. So similarly, there exists a delta 2 greater than 0. Since the limit of g is m, if x minus a is less than delta 2, then g of x minus m is less than epsilon over 2. Very nice. Yasmin knows what's going on here because we're going to add the two of them. Right? Remember, it's the limit of the sum that we're talking about. And now, very similar to the previous question we just did, where we took delta to be the minimum of 1 and epsilon over 5 because we needed both things to be true. Here, we're going to take delta to be the smaller of the two. Why do we know this conclusion? That's by the definition of the limit. The limit of g is m, so g can be made arbitrarily close to m by taking x sufficiently close to a. Here, the arbitrarily close is characterized by the epsilon over 2. Thus, for delta to be the minimum, if delta is the minimum of delta 1 and delta 2, then if x minus a is less than delta, then it's automatically less than delta 1 and less than delta 2. Right? So it satisfies both of these simultaneously. And that's very desirable. So if this is true, then what are we looking for? We're trying to show that the limit of the sum is L plus M. So f of x plus g of x minus the proposed limit has to be made less than epsilon. So what is that? Well, the limit of f is L, and the limit of g is m. So let's open up the brackets and group these things appropriately. I'm going to group the L with the f, and I'm going to group the m with the g. And now, the absolute value of a sum is less than the sum of the absolute value. And this is less than epsilon over 2. And this is less than epsilon over 2 as well. Right? Because x minus a is less than delta, so it's less than delta 1. And it's also less than or equal to delta 2. And of course, epsilon over 2 plus epsilon over 2 is epsilon. Beautiful. Lucas, absolutely. The minimum of the two is the smallest value of the two things. How are we doing here? I think we're doing very well, right? I think we have a lovely appreciation for this epsilon delta business. Or perhaps an appreciation for the limit laws instead of going through the epsilon delta business. Right? Am I right? Now people want to use limit laws instead of epsilon delta. For those of you interested, this whole epsilon delta definition business is part of Math 242, known as real analysis. And that's all you do in real analysis. You prove the foundations of calculus using the epsilon delta business. It's great stuff. Really very rigorous, demanding. And, you can spend years developing this thing. So you will not get any questions like this on exams. No epsilon delta stuff on the exams. Instead, let's move on. Let's move on to the idea of continuity. We say a function is continuous if you can draw its graph without lifting the pencil from the paper. Now that's all well and good. That's all well and good if you have the graph. This is a completely different topic. Moving away from the epsilon delta because it's not going to be on the exam. We've already spent more than enough time. Right, so very easy to determine if you have the graph. But as suggested before, here the idea is to draw the graph, knowing that your function is continuous. So we need a workable definition for continuity, at least locally. So what does it mean for a function to be continuous at a point. People, I cannot make it more clear. Epsilon delta definition will not appear on the exams. Definition: f of x is said to be continuous at x equals a if the limit as x goes to a of f of x, limit from the left exists, limit from the right exists, so the limit itself exists, and, well, I mean, let me spell it out. Limit from the left exists, and the limit from the right exists. So in other words, the limit itself exists and is equal to f of a. Daniel, I thought I had been very clear. Not sure why you're still having questions. It's not going to be on any exam. Not going to be. I'm not saying don't learn it. You can learn it. The more you know. So you see, that's the thing. The more you know, the easier everything else becomes. If you're comfortable with the epsilon delta definition, everything else is trivial. What does the min equation mean? It means you're taking the smallest value of the two, the minimum. Are they on the web work? I don't know. I don't know if they're on the web work. I don't think they are, but there could be one or two questions. Probably not. So here's the definition of continuity at a point. Let's take a few examples. Certainly, somebody's asking if continuous functions have domain. I mean, needless to say, right, your function better be defined at A. So absolutely. Yeah. And that's where the book is slightly wrong. But let's not discuss that immediately. Rather, let's move on to this question. So show that this function is continuous at x equals -2 using the limit laws. Because, you know, let me point out, since continuity is really a limit, and limits can be defined using epsilon delta definition, then you can very well imagine that there's an epsilon delta definition for continuity. I won't even write it down, but if you want to be rigorous, epsilon delta definition for continuity. I'll point out where the book is slightly wrong. It's a subtlety, but let's not worry about it for now. And, even though the book is a bit wrong, we're still going to go with the definition, with what the book says. That's the book we're using, so we're going to go with that. Show that this is continuous at x equals -2. What do we have to show? We have to show that the limit from the left, as x goes to -2, is equal to the limit from the right, as x equals to -2, is equal to the function evaluated at -2. Now, in this case, we don't have to take limit from the left and limit from the right, because you can probably easily see that the limit exists. Let's evaluate this limit. Well, exactly as Rachel suggests, you can plug it in if it's a polynomial. But here it's not really a polynomial because of this cube root. But you know by one of the limit laws that the limit of a root is the root of the limit, assuming everything exists. Right, so this is one of the limit laws. And now, as Rachel had suggested, now this is just a polynomial. So by one of the limit laws, the corollary, right? Limit of a polynomial is just a polynomial evaluated at the point. So we can just plug in. 4 times 4 is 16, plus 4 is 20, plus 7 is 27. So this is cube root of 27, which is 3. Isaac is saying, is it 4 to the power of -2? No, sorry, this is the blackboard here. Small, it's just 4 squared, 4x squared. Right, so we found the limit. So you know that the limit from the left and the limit from the right both exist and are equal, because the limit itself exists. And now, what is f of -2? Well, f of -2, you're just plugging in. So -2 squared is 4, 4 times 4 is 16, plus 4 is 20, plus 7 is 27. Cube root of 27 is 3 again. Plus or minus? Where are we going with that? So plus or minus 2. Ren, I'm not sure what. Very well. So there you go. We've evaluated the limit, and we got 3, right? So limit from the left and limit from the right both exist and are both 3. And the function at -2 is also 3. Everything is equal, and we're done. There you go. So the function is continuous at -2. Right? Continuity is not a difficult concept. It's really that the limit exists, and with one extra condition, that it's equal to the function at the point. Well, maybe I rubbed it off a bit quickly there, but let's talk about, right? Let's talk about what functions are continuous. As Rachel pointed out, one of the limit laws is that limit as x goes to a of p of x is p of a. If p is a polynomial, right, Fabian? If p is a polynomial, the limit is P of A. So polynomials are continuous. Everywhere. At every point. Similarly, rational functions, right? One polynomial divided by another. Rational functions are continuous everywhere they are defined. So somebody had brought up the idea of domain. Rational functions are continuous in their domain. Abhishek was asking about sine and cosine, but you know the graph of sine. You can graph sine without lifting the pencil from the paper. Sine x is continuous. Same with cosine. What have I drawn here? Here we've drawn an exponential function. You've drawn it without lifting the pencil from the paper. Exponential functions are continuous. Logarithms are continuous. Jonas is asking about tangent, but you know the graph of tangent. Right, tangent. And so on, right? This is the graph of tangent. And you can graph tangent, right? You can graph these pieces without lifting the pencil from the paper. Now, pi over 2 is not in the domain. 3 pi over 2 is not in the domain, and so on. So the tangent function is continuous in its domain. How can rationals be continuous if there are two parts of a rational function? Right? And let's generalize. Let's generalize the idea if f and g are continuous. If you have two functions that are continuous, the sum is going to be continuous, right? Think about what that means. Let's prove that quickly. You want to evaluate the limit of the sum, but you know that that's the sum of the limits. Right, by these limit laws. Since f is continuous, what is the limit as x goes to a of f of x? By continuity, this is f of a. Thank you. And by continuity of g, this is g of a. So you see the limit of f plus g is just f of a plus g of a. That function evaluated at a. Continuity. We're done. Continuity is what allows you to just plug in to find a limit. If you know your function is continuous, exactly that. For any continuous function, to evaluate the limit, we can just plug in. Is this proof only for polynomials? It is not. Here this is the proof for continuous functions. And the sum of two continuous functions is itself continuous. So an exponential plus sign gives you a continuous function. To show a rational function example, let's prove this. If f and g are continuous and g of a is not 0, then the quotient is continuous. And the proof is exactly the same. Not the limit of a sum, but the limit of a quotient. And you know what that is. By one of the limit laws, the limit of a quotient is the quotient of the limits, assuming the limit of the denominator is not 0. And now, since your function f is continuous, the limit of the top is just f of a. Since g of x is continuous, and g of a is not 0, the limit of the bottom is g of a, and you're good to go. Here, I've proven it for any quotient of continuous functions. In particular, one polynomial divided by another. As Daniel points out, the difference of continuous functions is continuous as well. So sum, difference, quotient, product. The product is going to be continuous. And the composition. The composition of two continuous functions is continuous. Let's illustrate with a few examples from the book. Questions are coming up as to what functions are non-continuous. What does a non-continuous function look like? Let's hold off on that. We won't have time to discuss that today, but I'm going to let you think about it. Question is asking us to explain why the function is continuous. In its domain. Right? Why is this function continuous? Well, this function is a rational function, and we know rational functions are continuous. Or it's one polynomial divided by another, and we know that polynomials are continuous. So either way, the result is the same, as long as you stay away from the denominator being 0. Consider this. Eddie pointed out that x squared plus 2x minus 15 is never 0. Very nice. And you prove that by showing it doesn't have any roots, right, using the quadratic formula. Very nice. So in fact, the domain is all of R. Very nice. Well, let's illustrate 30. 30 is a better, oh, no, b squared minus 4ac, or minus, right? So it could be 0. Very well. No harm done. Yeah, so number 30 is a better example of what you want to do, spelling everything out in complete detail. You know that if f and g are continuous, so is its sum. So really all you need to do is show that each piece is continuous. If you show each piece is continuous, then the sum of continuous functions is continuous. So let's start from nothing. 3x minus 2 and 2x minus 3 are polynomials. And thus continuous. Everywhere. From limit laws, the limit as x goes to a of the square root of 3x minus 2 is the square root of the limit. Assuming the limit exists, right? And here, this is just going to be 3a minus 2, and then you take the square root. So this function, square root of 3x minus 2, is continuous. In its domain. By the way, what is the domain? Eddie has given it to us. Thank you. X bigger than or equal to 3 over 2. Similarly, the cube root of 2x minus 3 is the cube root of the limit, which is 2a minus 3 cube root. So this part is continuous. In its domain. What is the domain? We're finishing up. This is our last example. What is the domain of this function? For what values of x is cube root of 2x minus 3 defined? Domain is all of R, thank you. And consequently, all of R because of the cube root, right? Even if it's negative, you can still find the cube root of a negative number. It's not an issue. So this part is defined everywhere. This part is defined on the interval 3 over 2 to infinity. So the domain is 3 over 2 to infinity. This part is continuous on that domain. This part is continuous on that domain, and consequently the sum is continuous as well. Pamela is asking, how do we know it's continuous if it's a polynomial in a square root? Well, by limit laws, the limit of the square root is the square root of the limit. And now this limit here is just a polynomial. So you can just plug in and you get 3a minus 2, and then you take the square root. And this is just that function evaluated at a. So that's the definition of continuity. Zuhair is asking if it should be 2/3 to infinity. I claim negative numbers are not an issue because it's cube root. If 3a minus 2 is negative, then we're in trouble, and that's why we are restricting our attention to the domain. So there it is. This part is continuous. This part is continuous, and consequently the sum is continuous as well. Isaac, I think 3/2 is the way to go here. All right, yeah, and we're done as well. Thank you all for coming. Naomi wants to know how we found the domain. We are looking at square root of 3x minus 2. When is this defined? And you know you cannot take the square root of a negative number. So you need 3x minus 2 to be bigger than or equal to 0. Bring the 2 over. Oh, it is 2. It is 2/3. It is 2/3. I had dismissed somebody's suggestion. Right, bring the 2 over and then divide by 3. So maybe, sorry, I did not want to confuse anybody. I should have done it. I was just reading off the answer. Eddie. So we need x to be bigger than or equal to 2/3. This is from page 124. Well, but I mean, if you're using a different book, it's what are we doing? We're doing continuity, continuous functions. I'm not sure what you mean by 28 wouldn't be continuous. What's 28? Oh, the rational function. Well, we don't want a 0 in the denominator. Exactly. So the domain would have been all real numbers, except I think somebody worked out, is it +5? +5 and -5? -5 and +3. Elliot is bringing up an excellent question. Would we say square root of 3x minus 2 is continuous at 2/3, even though the function is not defined on the left of that? I'm going to let you think about that. We'll discuss that on Friday. You're right. It's a question. It's a question that arises naturally. We'll discuss it on Friday. Exactly that. We're trying to prove using limit laws that a function evaluated at a limit just ends up being the limit of a function is just a function evaluated at the limit. We can do that if we know the function is continuous. I am using the 9th edition, and yes. If you're using another edition, continuity. There's a whole section on continuity. That's what we're doing. Well, whatever that continuity section refers to. I'm going to go ahead and say 2.5 if that's what you have noticed. Well, here we're talking about cube root, right? And cube root of a negative number is not an issue. So as opposed to the square root where we needed the argument to be bigger than or equal to 0, in a cube root, it's not a problem. Anything goes. Positives, negatives, we're all good. Normally I do teach 141. I will not be teaching it in the winter. Well, at least I'm not scheduled to teach it in the winter. But you've got excellent teachers there. They will teach you everything you need to know. Abhishek is asking what we've done so far. I mean, I want to say we started from essentially 2.1 and we're now 2.5, whatever that is. I mean, I think we've done everything in chapter 2 so far. You should attempt most, if not all, the questions. Absolutely. Yep. All right. That's enough. Thank you for coming, folks, and I will see you on Friday. Have a good one.